Okay, thank you. My handwriting was very bad in that sentence. So obviously, since I've given this talk approximately 50 million times before, as you can see, this means I don't need to prepare, and that if I just rock up at 5 past the hour, it will probably be fine. Okay, important question. Has anyone done a MSP 101 so far this year on lenses and things like that? That's a no. Okay, so I'm going to have to spend half of my time talking about this by necessity, I think. So my goal is just to give everyone a approximately general idea what open games are and how they work and the kind of things you can do with them. It's incredibly necessary to cut corners because there's lots of fiddly details. But this is fine. And the thing that makes this somewhat feasible is everybody here knows what a monoidal category is. By which I mean, if you don't know what a monoidal category is, sorry, I can't help you. I have to assume something. Otherwise, we'd be here for 5 hours instead of 4 hours. Okay, so there is a rather interesting monoidal category. There is things in the chat. I am not going to keep up with the chat, so please shout at me if you have questions. Okay, that's the deal. Okay, there is a category called the category of lenses whose objects are going to be pairs of sets or pairs of types, or however you like to call it. And I'll call these x, comma, x prime, and morphisms from x, comma, x prime to y, comma, y prime are going to be pairs of functions where, let's call this lambda, and we're going to have lambda 1 is going to be a function from x to y, and lambda 2, this is where things get a bit tricky, is going to be a function from x cross y prime to x prime. So this is a bit weird. So the first thing is pretty straightforward and goes forwards as makes things easy. The second thing is weird in two ways. One is that it goes the wrong way, it's contravariant, and the other is that it has this extra dependence on x. So this is like a more interesting version of set times set up, where the up part also has this kind of partial dependence on the forward direction. And Connor just did a very dramatic zoom out, which was funny. Okay, so I claim, and these pairs of functions are called lenses. So this category is named after its morphisms. And I claim this is a category, which means that this thing had better have identities and an associative composition. So we have so for every pair x, x prime, we have an identity from x, x prime to x, x prime, which is the identity from x to x, and the projection. Oh, I can do this. That's a neat feature. Okay. And the projection from x times x prime to x prime. Slightly more gnarly is if I have a pair of these things, x, x prime to y, y prime to z, z prime, I need to tell you how to compose them. So, well, the forwards direction is easy. We go x to y to z. That's pretty straightforward. In the backwards direction, you have to do a little bit of type-directed programming. So we have an x and a z prime, and we want an x prime. So how can we get an x prime? Well, we can get an x prime from lambda 2. if we give it an x and a y prime? Well, we have an x, well, that's easy. So how do we get a y prime? Well, we can get a y prime for Mewtwo, that's a Pokemon, if we have a y and a z prime, and we have a z prime, but so how do we get a y? Well, we can get a y from lambda 1 if we give it an x, and we have an x. We've already used the x, so we're using the x twice here. So this is saying that lambda mu 2 of x and z prime is given by lambda 2 of x together with mu 2 of lambda 1 of x and z prime. So that's the characteristic composition law for lenses. And I require you to take it on trust that this is associative. It is not, to me, obvious that this is associative, but by some kind of miracle, this is associative, and this thing is the unit on both the left and right for it. So these things form a category, which is rather nice of them.
Yeah, I suspect that kind of up to brutal jiggery pokery that indeed Agda knows it's associative, and it's probably very difficult to write anything well typed where it isn't associative. I think it's useful to think, at least with one metaphor, of these things as being about kind of question and answer.
Yeah.
But there's sort of and the morphisms are about what happens when someone asks you a question and then you phone a friend.
So in string diagrams world, this is how I draw these morphisms. In these pairs XX prime, I distinguish the first things in the first part of the pair by being labeled going forwards, and things in the second part of the pair being labeled as going backwards. And a lens, so the slightly more involved version of what Connor just said is that a lens is describing a strategy for the interaction of this system with an environment around it, according to the protocol, where first the environment or the opponent gives it an X. So it inputs an X here, it has to reply with a Y. So the strategy for that is a function from X to Y. Then the environment replies with something in Y prime, and it has to respond with an output in X prime, but it still remembers this X. Okay. What else can I say? This category is importantly monoidal according to X prime tensor Y prime is going to be given by X times Y comma X prime times Y prime. Although sometimes I use the convention Y prime. Yeah, this is right, Y prime times X prime. On morphisms, this turns out to be the only obvious thing. It's less interesting than the sequential composition.
Yes, so here monoidal means you can do it in parallel.
Monoidal means you can do it in parallel, and this monoidal product is not a Cartesian product. So it's kind of interestingly monoidal. Let me just talk about the various generalizations of this thing. So I've defined lenses over the category of sets. So objects are pairs of sets, and lenses are built of a pair of functions. You can straightforwardly generalize this to being over any finite product category. There are these generalizations that I'm going to talk about turn out to be useful in open games world. There are two classes, big classes of generalizations of this, which are both interesting. One is to what we call optics, which is a non-obvious generalization of lenses that work if your finite product category is not a finite product category, but it's just monoidal. So over a monoidal cat. This is not obvious how to do it. but you can do it, and I won't say any more about it. It's quite important because game theory typically involves lots of probability, and categories of probabilistic functions are characteristically not finite product categories because a joint distribution is not determined by its marginals. Okay. And the other generalization is a thing that is variously known as dependent lenses, aka morphisms of containers, which is a much older name for this, exactly the same thing on the nose, studied by people such as Connor and Neil that have been knocking around in the historical predecessors of MSP group, aka up to equivalence of categories, natural transformations of polynomial functors. That's another highly non-trivial equivalence. So these are two different generalizations of lenses, both of which are useful in game theory.
So the thing there is that if you allow, in some sense, the type X prime to depend over the value in X and the type Y prime to depend on the value in Y, you know, that's to say what the sensible answers are depends on what the question was, then the sort of need to remember the X in order to deliver the X prime becomes rather crucially well motivated. Like you couldn't even talk about what the X prime was supposed to be unless you remembered the X.
Yeah. Okay. I need to keep going at quite a pace to say anything remotely resembling game theory at this speed. But yes, and one of the fun things that we're doing on our side of MSP group is trying to unify these two generalizations of lenses, which involves lots of interesting and brain-melting category theory. Okay. So what the heck does this have to do with game theory? So there are several different inequivalent classes of definitions that we label open games. And I'm going to tell you about a well-chosen middle ground that is about halfway between the original definition of open games, if you look it up in my PhD thesis, versus the most cutting-edge version that we've been working on this year, which I'm going to leave for other people to talk about. I assume somebody's going to be talking about Parrot Optic at some point. I'm not planning to talk about that. An open game, so an open game of type x prime to y prime. So these things are again going to form the morphisms of the category. Consists of three things. The first thing is going to be an index set. So we're going to call the elements of this index set strategy profiles. The strategy profile is going to be like a description of what the players in your game are going to do during the play. So strategy profile in game theory means essentially a contingent plan for what every player is going to do in every possible scenario that can arise during the game. But for now, this is just going to be a set and it's going to behave like an index set, which is quite nice of it. The second thing is we're going to have a sigma indexed family of lenses of the same type. I just realized I have switched convention from writing these horizontally to vertically. Sorry about that. I do both. Here we go. So one of the things that an open game is it's essentially a labeling by sigma of a bunch of lenses of the same type. Okay, so this is increasingly mysterious. I'm going to give you a whole heap of examples, I hope, after this. Now, the third thing is an equilibrium. That squiggle is supposed to say equilibrium function. And this is going to return one of two elements that says either, yes, I am a Nash equilibrium, or no, I'm not a Nash equilibrium. So in classical game theory, equilibriumness is a property of strategy profiles. So a strategy profile can either be an equilibrium or not an equilibrium. That's for an ordinary game. An open game is supposed to be an incomplete description of a game that is waiting to be put into an environment that surrounds it. And if you don't know yet what environment you're going to be in, you don't know whether your strategy is good or not, because important things like your payoffs can depend on the action of an environment that you haven't been given yet. So the equilibrium function is going to depend on something called context or environment. And this is going to describe everything that's missing, everything that you need to turn your open game into an ordinary game. And this is going to, by a series of small miracles, is going to turn out to be a pair of functions of an x, an element of x and a function from y to y prime. And this is essentially a series of miracles that makes this happen. So here the x describes the initial state that your game is in, and the function for y to y prime describes something like what your payoffs are going to be given the actions that you take during the play. Okay, this is pretty mysterious. So this, I'm starting to say words that sound like game theory, but it's not supposed to be clear yet what this has to do with game theory at all. I assume you can all see this downloaded document with corrupt thing at the bottom. I have no idea where that comes from. This is just remarkable doing its thing.
The level of corruption in this talk is...
Yeah.
Try my best.
You're simultaneously accessing the Pandora papers.
Yes.
Or is this the Tory party conference? No.
Yes. Sometimes simultaneously. Okay, so here's basically the important example. By the way, I mentioned these things are going to be the morphisms of a category. It's not obvious yet how these things compose. I'm going to come to that later. A series of miracles occur that make the composition very nice once you look at it in the right way. So this will be an open game describing choice of y by a rational agent given x, given an observation of x. So this is going to be a player in a situation where they observe a value of x and then they choose a value of y, and they are choosing a value of y in order to optimize some payoff that they get. So this is going to be an open game of type, I'm going to call this D for decision. It's going to have type x, comma 1 to y, comma real numbers. Okay. So I have to give these three pieces of data in in order to define D. So the first thing is, what are the strategies? So the ways in which a player can choose a y given an x are functions from x to y. So I'm going to choose sigma to be the function set of functions from x to y. X and y here are going to be non-empty finite sets, just to avoid some annoying complications later to do with optimization. Now, the next thing we have to do is give a function, so a labeling of lenses of this type by sigma. So what we're going to do is we're going to send a function. So given a function from x to y, we need to produce a thing, a lens of type x1 to y r, and this is going to consist of, so we need a function from x to y, that's going to be the same f we were given, and we need something of type x times reals to 1. Fortunately, we have a unique map to 1, so let's delete. Okay, so the question is, what the heck is this R doing here? Because we haven't actually used it. The only thing we've done with it so far is deleted it. So that was the only thing we could do. And the answer is in the third thing. Oh God, I'm not plugged in. Okay, laptop rescued. So the third thing is going to be we need to say true or false, given a function from x to y, a point of x, and a function from y to r. And this is supposed to say, is this a good strategy or not? So given f, our strategy from x to y, and the thing that tells us what state we're in, that's some x, and a thing from y to r, and this is where the magic starts to happen. So this thing behaves like our payoff function. This is the thing where the environment responds and tells us how much we get paid for the choice we made. And then, so we have to say true or false, and we're going to say true if and only if and only if our strategy in its current state, so this thing is in y, maximizes k. So in other words, if in our current state, our strategy tells us to do something which gives us a payoff at least as high as anything else we could have done. Okay. Now, so I want to build up to showing you what an actual game looks like, even a very straightforward one. A two-player simultaneous game like Prisoner's Dilemma. So I need to tell you how to compose these things. So here's the important thing. This is the miracle about x times y to y prime. So this is this thing called contexts. It turns out that x is the same thing as lenses from 1, 1 to x prime, because a lens from 1, 1 to x prime consists of a function from 1 to x, which is an element of x, and a function from 1 times x prime to 1, which can only be delete. The other thing is that the function set from y to y prime is the same thing as lenses from y prime to 1, 1, because a lens from y prime to 1, 1 consists of a function from y to 1 that can only be delete, and a function from y times 1 to y prime, which is a function from y to y prime. And by the way, so 1, 1 is the monoidal unit of this monoidal category. So these things are called, in standard categorical quantum mechanics terminology, these things are called states, and these are called co-states. So the slogan is like, in the monoidal category of lenses, states are like states in set, they're just points. Whereas co-states are very interesting. They're these, like, I call them continuations, just to be unnecessarily scary. They're functions that happen after you finished. Okay. So now given this trick, I can tell you how to compose these things. So if I have an open game XX prime to y prime and another one to z prime, so I'll call this curly G, this curly H. I need to tell you, how do I define the composite given the parts? And basically the only decision that I have to really make that isn't forced is to tell you that the sigma is composed by Cartesian product. So sigma of GH is going to be, by definition, sigma G Cartesian product sigma H. So that's going to tell you that a strategy profile for a composite game is going to consist of, by definition, a strategy profile for one and a strategy profile for the other. Now, given this decision, everything else is basically forced. So, so a pair sigma tau had better label a lens from XX prime to ZZ prime, and it's going to label specifically the lens labeled by sigma given by G, followed by, given lens composition, the lens labeled by tau for H. So that's the only thing it can be. Now, now for this thing, this is where it gets fun, because what we have here is a sigma tau pair. That's our sigma for GH. We have an X and we have a K. And X is in X and K is a function from Z to Z prime. But we don't care about that. We're going to call this a lens from 1, 1 to X, X prime. And we're going to call this a lens from Z, Z prime to 1, 1. So you can kind of imagine we're kind of extending this sequence of compositions here. So X goes here, K goes there. And we have to say true or false. So what we're going to say is the thing given by, so I'm going to call this E sub G. I didn't actually name any of these things, which wasn't very smart of me. E for the equilibrium function. So we get a true or false given sigma and a context for G, and that's Boolean and, so we're just taking and in the two-element Boolean algebra. Tau is an equilibrium for H in a context for H. Now we have to build contexts for G and H. So how do we do that? This is where the magic happens. So, well, X is still a valid thing for G because it's still, so for X, we need to get a map in from 1, 1, which we have, that's X, and we need to get a map out to 1, 1. Sorry, that's from here. And what we can do is go via H. But we need we need H as a lens, not as a game, but that's okay because we were given tau. We have a tau lying around. So this thing we have is the lens H tau K. So that's this lens composition, this lens. And you can imagine writing that directly in terms of functions from Z to Z prime is not so pleasant. Going the other way around, we need, so our K is still valid, it's a map. It's a lens out of Z prime. We need a lens into Y prime, which we can do by X followed by G of sigma. And now I've magically defined the composite for you. And you can see there's a kind of cross terms going on because sigma appears both here, and tau appears both here and here. And that's kind of characteristic of game theory. It's like if you look at the definition of Nash equilibrium, you get these kind of cross terms. It's kind of it's a fixed pointy thing. Okay, and the other nice thing about writing it like this is that if you believe me that lens composition is associative, then it's completely obvious that this thing is associative. I mean, it's associative up to rebracketing this Cartesian product, which is a non-issue. This is a stupid problem, not an interesting problem. This part, which is the actually non-trivial part, doing it this way makes it like blindingly obvious that this thing is associative, which is really nice. If you look up those proofs in my thesis, we didn't know about lenses at the time, so they're deeply unpleasant and done by hand. Okay. Now, at this point, I'm going to have to say there is also a monoidal product of open games, which is basically the same idea, but just a little bit different. There's no like highly non-trivial new ideas in the monoidal product. It's just a bit different. Like at this point, you could probably invent the monoidal product. What this means is that now we can start to build examples where I can draw a string diagram like this. X reals, Y reals. So this is a bona fide string diagram corresponding to a morphism in a category that looks like D1 tensor D2 compose U, where D1 and D2 are going to be examples of this definition, both with X equals 1. So this is a choice of something given an observation of nothing. It's just instantiating this for X equals 1. Because there's nothing here. This is a string diagram, so this empty space means the monoidal unit, which is 1, 1. And this U is a lifted function. So it's another example of an open game that's much more boring than the D's, given by sigma of U is going to be a one element set. So U is going to be the payoff function. The payoff function cannot make strategic choices, so it's not going to have any strategies. It can only do one thing, which is to be itself. Its equilibrium function is going to be always true no matter what. And that's a bit of a gnarly thing. The way I explain this is to say that Nash equilibrium is like a negative condition. You are in Nash equilibrium if no specific player has kind of positive incentive to deviate and do something different. So a utility function is degenerately in Nash equilibrium because it doesn't contain any players, so there is nobody to be unhappy. The real answer is that we're composing it with and, so it had better be true, otherwise it just kills everything.
That explains the kind of calculus flavor of the utility composition or the equilibrium composition. You're basically asserting the non-existence of the place where the unhappiness is.
Interesting. Yeah.
Right. You're saying that the one home context site where things go wrong does not exist.
Yeah. Yes. Now the other thing is you need to be a labeling by the one element set of lenses, and so this object here along this boundary is really x times y comma r squared, because as I said, forwards arrows mean thing in the first element of the pair, backwards arrows mean the thing in the second element of the pair. I'm secretly applying a symmetry because everything is symmetric monoidal. So we need a lens from x times y r squared to 1, 1. And we have already established that lenses with a type like this are the same thing as functions from this to this. Because this is given by a function from x times y to 1, which can only be delete, and a function from x times y times 1 to r squared, which is a function from, and this is going to be our favorite utility function. So, for example, if you really like the prison's dilemma, you can choose x and y to both be the set of cooperating defect, and this thing to be the payoff function of prison's dilemma. The string diagram here is hardwiring the number of players and the kind of dynamic structure of how they interact. Things like the number of choices and the payoff function get kicked into whatever's defined by these labels. So that comes over here. Okay. And then we're going to do a bunch of composition according to some composition rules, which I have partially told you and partially not told you. And what it's going to turn out is that sigma of the game denoted by this entire diagram is going to be up to isomorphism, because everything is up to isomorphism here, x times y. So that is the strategy profiles for this game is just a choice for one player and a choice for the other player, because nobody can have their strategy contingent on anything else, because we haven't wired up this diagram so that anyone can see anything. So these are both kind of one-shot choices given no observations. The lens denoted by this thing is necessarily trivial because this diagram is closed. It has no boundary. So this, no matter what, we have to be a lens from 1, 1 to 1, 1, and there is only one of them. So that goes away. The interesting thing is the equilibrium function. So given sigma, which is an XY pair, and a context, and it turns out that for similar reasons to why there is exactly one lens of this type, there is also exactly one context of this type. So that also goes away. So I'm skipping over a lot of stuff very quickly here, but the slogan is that when your diagram is closed, most of this machinery basically goes away, and you're left with something that looks like a game in the ordinary sense. And then it turns out that you can just calculate that this thing is true if and only if x is in the argmax over x primes of u1 x prime y, and y is in the arg max over y primes of u2 x y prime, aka xy is a Nash equilibrium for the game whose payoff function is u. So that's the am I still here? I feel like I've frozen.
No, you're
there.
Oh, okay. Everything just caught up very quickly. Okay, my internet connection is a little bit sketchy. Okay. All right. So that's the punchline is that well, the stuff like Nash equilibrium falls out as a kind of composite thing given these lower level things. Okay, now I have, let's say, 7 minutes. So one thing I can say is you can do a lot more with open games than just game theory. And a lot of what we're working on at the moment is basically answering the question, what other cool things can you do with this type of machinery? Namely, like indexed families of lenses and another thing. Yeah, the other thing is like the equilibrium function. And in general, we replace this two. This two is saying either yes, you're a Nash equilibrium, or no, you're not a Nash equilibrium. But you have quite a lot of scope to fiddle with this and change it to other things. Like this can be an update to sigma, for example. And you can start to do cool stuff. So this is when things like machine learning come into it. Okay, this is left for other people to talk about. Now, what I want to do with my remaining, according to my clock, it's still 7 minutes, is show you to codes, because we have an implementation of this thing. And so let's see where this goes. Okay, I'm going to stop share and I'm going to reshare with full screen this time. I'm going to outrageously hope I've got nothing on my screen that nobody should see. Okay. Oh, I'm in the right place. I'm on the right branch. Let's see if it, bugger. Wait, what?
That
Oh,
looks like a
good.
merge
Okay,
conflict.
fine. Okay, I'm not going to show you this running because apparently we have a conflict in the Cabal file from left over from last week. That's what I get for not preparing. So I'll be able to show you the codes, but not the running. Actually, if I switch to check out test, oh, bugger. I hate Git. Okay, I'll show you the code. So here there are 100 extra complications. So this data structure here is the equivalent of lenses, where we also, so this is when I said there are optics over a monoidal category, and I'm not going to tell you about them. This is a bit like what it looks like. So this is a probability monad. We do some stuff, but in the end, these things are the appropriate generalization of lenses that have some extra features baked in. The actual definition of open games is so heavily buried in this code and so heavily abstracted, it's probably not worth showing. But what I can show you is what examples look like. So in pen and paper, we draw string diagrams to denote morphisms of this monoidal category. So, and a string diagram means an expression in terms of the kind of language of composition and tensor. In a computer, we can't draw string diagrams because programming is difficult, and as someone that has put considerable thought into building a string diagram editor, it's not worth it. So instead, we would like some other higher level language that's roughly equivalent to string diagrams, but is ASCII based. So that's what we have. So let's see. And this is what things end up actually looking like in practice. So matching pennies is just another biometrics game. It's like Prisoner's Dilemma or whatever. And we end up with basically a domain-specific programming language where we have a sequence of, so each of these blocks is describing the equivalent of a string diagram element. So in this case, each of these blocks is describing a decision by one player. And what this is saying, so how to read this? Well, there's some stuff, we're naming the players, we're giving the list of choices that the players have available. We are binding the choice that they make to a variable, and then we are feeding back. Why the heck is there a $sign in there? I didn't write this, I think. This is just a Haskell function of X and Y, which are the two choices. And everything else is written in, this is just Haskell. So this is the payoff function of matching pennies written in Haskell. This thing is a domain-specific language that compiles to Haskell, and the current version of the compiler is written by Andre, who may or may not be in the audience. What else do we have? Here's a mildly more interesting example. We have, of course, changed syntax from the previous file to this file because obviously we have more than one syntax, because otherwise life would be easy. And where's the fun in that? So this is still a simple but a much more interesting example where so there's a lot more kind of non-trivial probability, Bayesian probability going on, where we have a seller and a buyer, and the seller is selling a used car, which can either be good quality or bad quality with probabilities in ratio 1 to 4. So we're drawing from a probability distribution here. And then the seller is choosing to charge either a low, so the seller is observing the quality. This is an observation of the quality of this variable, the quality, and then choosing low or high, and that choice is bound to this variable. And then the buyer chooses buy or not buy after observing the price, which is low or high, but not observing the quality. So then the buyer has to infer a signal about the quality given the price using Bayesian reasoning. And that's all happening behind the scenes here. And then there are payoff. So there are payoff functions which depend on all three: the quality, the price, and the buy or not buy decision. And again, that stuff is written in just ordinary Haskell. I guess I will leave up, since I'm out of time, I'm just going to leave up a complicated example on the screen from ongoing work in progress. This kind of stuff. This one's much more interesting because each of these blocks is now referring to, these themselves are non-trivial open games which are defined in other files. So that's the point of the exercise, is we do all this category theory and then we get something that you can't do without doing the category theory. Namely, you get compositionality. So we're actually, by this point, we're actually reaping benefits from all of the crazy theory. And And I am out of time. I hope I've been able to at least say something of the flavor of this stuff, which is all I could ever have hoped to do. Yes. Throw questions at me.